can see, I am not at the chalkboard today. Seems like most people were attending online, so it's just as easy for me to do it completely on Zoom, and this frees up the room for somebody else. So I hope nobody minds. I hope none of you accidentally turned up there this morning. Okay, so I will continue where Tristan left off. Thanks to him for filling in for me last week while I was at the conference. So it's my understanding that he covered some more things about positive elements and didn't quite make it to hereditary subalgebras. So that's where we begin today. And I'm just going to continue using the numbering system that was in the book, because I'm following that. And if you want further information, I suggest you look there. So it probably won't be quite consistent with what Tristan was doing last week, but hope this makes it easier for me, because when I refer to things from previous weeks, I can easily look up what the numbers are, even if I haven't found my notes. Okay, so without further ado, let's get started. So we start with a definition. And that is, of course, exactly what the title says, which is a hereditary subalgebra. So a C-star algebra, well, let's start with the C-star algebra A. And we don't mind if it's unital or not. And if we have a C-star subalgebra E, so that's going to be a C-star algebra inside of A that's closed with respect to the norm of A. And of course, it's got to be self-adjoint. So B in A is called hereditary. If whenever we have an element B in A that's self-adjoint, and element A in self-adjoints of A such that A is less than B, then A must be also in B. So this is hereditary with respect to this partial order that we defined on the self-adjoint elements. So we really see that with C-star algebras, where we're able to define these positive elements, we get these sort of extra structures that we can examine, in particular these hereditary subalgebras, which play quite an important role. So the first kind is called a corner. So if we take a projection, so recall that that just means it's self-adjoint and idempotent. Then we can form what's called the corner. And you may think, well, why is this called the corner? And if you think maybe just of matrices, and your projection P is, say, the projection that has just ones here, then if you multiply on either side by this projection here, you're just going to get this smaller matrix algebra in here. So it is literally a corner in this picture. Okay, so we have the following theorem, that this is in fact an example of a hereditary subalgebra. Okay, so how do we prove this? Well, the first thing to check is that it's actually a C-star subalgebra, and that's not too difficult. So if we have X, Y, and PAP, then there exists some A and B in A such that X is PAP, Y is PBP, and then it's easy to check that X plus Y is just P of A plus B, which is certainly in PAP. And similarly, XY is going to be P squared BP, which is actually just PAPB since P is a projection, and that's certainly in PAP. The star, that's easy to see because P itself is a projection. So we take the star of this. What does the star do? It puts everything in the opposite order and takes the star. Oops. But of course, P, as we said, is a projection. So we just get Px star P. And indeed, that is, again, in our corner. So this tells us that we have a star subalgebra. So we need to check that it's closed. So suppose we have some sequence in PAP, and it converges to some X in A. Well, how do we see that this is in PAP? Well, note that anything that's in PAP, since P is a projection, satisfies PXN. P is just, again, XN. So we get that PXNP converges to PXP, but since this is actually just XN, well, this also just converges to X, so we see that those are equal, and indeed, PAP is closed. Okay, so now the more important part, we want to see that it is hereditary. So let X be a self-adjoint element. And let Y be just some self-adjoint element that we assume is just an A at the moment, which is smaller than X. Now, what we need to show is that Y is in PAP. So first of all, we note that we can write any self-adjoint element, so in particular X, as the sum of two positive elements, this X plus and X minus. So remember, our self-adjoint element under the functional calculus looks like this guy. So X plus is this, and X minus is this, and they add up to X, they're both positive. And clearly, if Y is smaller than X, then it's smaller than X plus. So I should say that, okay, a priori, this is maybe just done in A, but we already know that PAP itself is a C-star algebra, so we can do this decomposition in PAP. Okay, so we can assume that X is greater than 0. Okay, so now we have Y less than Y less than X. And let's first assume that either Y or minus Y happens to be positive. Then since y is less than x, recall that we saw that we can multiply on either side by an element and its star. But in this case, we're just going to do a positive element, so we can multiply on either side by this 1 minus AP, and this preserves the order. And as we noted before, PXP is of course equal to X. So if we multiply this out, we're just going to get 0. And so if either y or minus y is positive, then we get that this is 0. Okay. So we can now show that y to the half 1a tilde. Oh, by the way, just recall that a tilde, this is unitization. So we haven't assumed that there's a unit in a, but note that all of this is still happening in a itself. So we're allowed to do this. So let's see what this is. Well, we can use the C star identity, and that gives us. So remember that we have a star a is a squared. So that's all that's all I'm doing here. And I'm using the fact that, for example, 1a minus p is positive, as is y, by assumption at the moment. So we get this, which is 0, which tells us by positive definiteness of our norm that this is 0. So y half is equal to y half p. Similarly, we can show so I'll let you fill in the blanks here. We can show the opposite just basically by taking the star of everything and using the fact that these are all positive, that y half is also equal to p y half. And multiplying these two things together, we get that y is equal to p y half p, which is just pyp. So we see that indeed in this case, our element y is in PAP. Now for the general case, if y is just a self-adjoint, we can again write y as the combination of two positive elements. So y plus y minus positive. Then if y is less than x, we get that y half plus y half. Again, we know that we can multiply on either side by a positive element, and the order structure doesn't change. Okay, now remember that when we do these, y plus and y minus, as you can see here, so this is, remember, this was x originally, but oops. When you multiply them together, we get 0. Which means that what is this value? Well, it's just y plus squared. Okay, so again, let's now multiply on either side, this time by the norm of y. Okay, I guess we need to square it there. Now note that y plus half over y, this is less than 1. So we get that this is less than x. And now we're back in the situation of the previous case, because this guy is just positive, which tells us that by above, this itself is in PAP. And of course, we saw that this is a C star subalgebra. So we can certainly multiply to get rid of this norm of y squared. And then we know that square roots of positive elements exist in C star algebras. So we get that y plus itself is in PAP. And then a completely analogous argument tells us that y minus is in PAP. And so we see that y itself is in PAP.
So Karen?
Yeah.
So I think in the definition of hereditary C subalgebra, the y is already positive, no? Like you show that if 0 is less than y is less than x, then y has to be within the hereditary.
Well, I suppose it's the same thing, but I suppose I defined it as self-adjoint. But it's clear that it amounts to the same thing. So I could have,
I'm not sure it does though, because 0 is in any C star subalgebra. Any negative of a positive element would therefore be in your hereditary C star subalgebra. So I think it has to be just for positive.
Any negative would be in, but if you have a positive element, oh, I see. You're saying that if then B is less than. I might have to think about that.
Yeah. Anyway, I think it's just sort of the definition. So once you prove the positive case, I think you're probably done. But yeah, anyway.
Well, since I'm sitting here at my computer, why not just Google it? On the other hand, doesn't this proof seem to suggest that if y is actually self-adjoint unless then it's in there, no?
Yeah, well, I wasn't sure about the argument you were doing before, where you assumed that y was negative, right?
Well, here we have, let's see. If y is negative, then you're saying that this is less than 0. Yeah, perhaps.
Anyway, the proof you did certainly covers it for the positive case, which I think is all you need.
All right. Just a second. All right, it seems you are correct. Sorry about that. So let me change, whoops. Right. So you're saying A needs to be in plus as well?
I think
Yeah.
so. I think it's like if 0 is less than or
Yeah,
less
that
than
makes
A,
more
then
sense.
yeah.
All right, so continuing along. So if we take any positive element, then we can find ourselves a hereditary subalgebra. First of all, by taking a little a closure, and this is going to be the hereditary C subalgebra generated by A. And if B and A is any separable, hereditary C subalgebra, then it's always of this form. Okay, so I guess with Tristan, you covered approximate units. Is that correct, Tristan?
Yep. So we covered approximate units, increasing approximate units, strongly, strictly increasing approximate units. So yeah.
Excellent. So this is going to be an approximate unit. Then we see that U lambda is certainly, oops, I did that the wrong way around. It was certainly not necessarily in there. Let's try that again, Karen. The problem with doing this at home means that I didn't finish drinking my coffee. So, all right, so this should be that AU lambda A is in, well, in fact, it's not even in the closure, it's just in there. So then when we take the limit, we get that A squared is in the closure. Which means that the C star algebra generated by A squared is in this AA. And by the fact that we can take square roots in here and uniqueness of the square root, we get that A is in there. So that proves the first claim there. Now let's see that it's hereditary. So if B is smaller than A, then we saw, well, actually, I don't know if we did see this, but B half is less than a half. Did that get covered? Maybe not. So this uses the fact that so this is true that b to the half is less than a to the half. So again, using our approximate unit. Oh, maybe I want even, do I want a quarter here maybe? Sorry, my notes are a bit messy. Okay, let's stick with a half. And maybe we don't even need a half. All right, this theorem is still true though, so so what is this 1 minus a tilde? Again, a is positive. So a looks like this. And then 1 is like this. So 1 minus a over n is something like this, which converges to 1. So we get that this is going to 0. Thus, we see that the limit again, using the C star equality. Oh, let's actually just do this. Sorry, I am being a bit of a mess. Let's try that again. So this here implies that which is the same as this should be a B, sorry. And then we do essentially the same trick as last time, and we also get that b to the half is the limit. Which then implies that b is in this closure, just multiplying b half together. So indeed, this is the hereditary subalgebra generated by A. Okay, so now suppose that B is separable. Whenever you have a separable C-star algebra, then in fact you can always find a countable approximate unit. And I don't know if this was defined by Tristan to be consisting of positive elements, but if I don't say otherwise, I mean that it's increasing and positive.
I think I specified that it's positive, consists of norm, elements of norm at most one. Didn't necessarily have to be increasing, but you could always find something that is increasing.
Okay. So, I mean, I guess increasing doesn't really matter here anyway, but now, if we're assuming these guys have norm at most one, then this guy certainly converges. And since B is closed, that's going to be in B. And then we see that well, so in particular, oh, I guess we assumed that already, that UN is in there. So since this is the approximate unit, this also tells us that UN is in A. And so A is what we wanted. Suppose you could also do this by, it doesn't really need to be a countable approximate unit. You could just take a countable dense subset of positive elements of B, and that would work as well. Okay, so now we're going to see that hereditary subalgebras are in one-to-one correspondence with left ideals in A. So this is going to be a closed left ideal. So if I say ideal, I usually just mean two-sided closed ideal, but I'm specifying that this is actually just a left ideal. Then I has a left approximate unit. Which is to say that if we multiply on the left with some element in A to this approximate unit, I guess I should have said that U lambda is the approximate unit. Then we just get back A itself. So let's see this. So first thing to note is that if we take I and intersect it with I star, then this is going to be a C star subalgebra. So that's not so difficult to check. This has made it self-adjoint. And of course, I is assumed to be closed and also closed under multiplication and addition. So that's fine. So we can find an approximate unit. So multiplying this out using the C star equality, all of these guys are happily living in our I here. So that's going to be 0. And then I suppose the last thing to notice is that if A was not in I, but in fact in A, then, well, that's in I because I is an ideal. Okay, so now we come to the correspondence between left ideals and hereditary subalgebras. So we have a one-to-one correspondence. Between closed left ideals and hereditary subalgebras. And that's given by the following. So if we have a left ideal, we'll see that I intersection I star is a hereditary subalgebra. And if we have a hereditary subalgebra, then we will show that the following is in fact an ideal. Okay. So what do we have to show? Let's take a closed left ideal. We want to show that I intersection I star is hereditary. So take a positive element in I intersection I star. Since I is a closed left ideal, there's a approximate unit. a left approximate unit. And if A is in A plus with A smaller than B, then we have that 1A tilde minus U lambda A is going to be less than 1A tilde minus U lambda B, 1A tilde minus U lambda. And that's for every lambda, of course, which means that doing the same trick as before, this A half. So this is just applying the C star equality. I'm skipping a few steps. So this is this guy is going to 0. So since eyes seem to be closed, we get that A half is in I. So of course, then A half, since I is an ideal, is also in I. Okay, so now suppose we have a hereditary subalgebra. And we'll put I to be this set here. So let A be an element of I and B be in A. And since we can always multiply by scalars without loss of generality, we can assume that B has a norm at most 1. So we want to show that AB is in I, which means that we have to show that AB star AB is in B. So what is this? That's B star A, B. B is less than or equal to 1, which means that this is less than or equal to A star A. So since B is hereditary, big B is hereditary, we see that AB star AB is in B, which by definition means that AB is in I. So I is an ideal, a left ideal. And then it's straightforward to check that the closure of B will imply that since B is closed, I will be closed as well. And indeed, this establishes the correspondence. And then it's easy to see that, in fact, these maps here are mutually inverse, which gives us the one-to-one correspondence.
So Karen, maybe I missed it, but did you show that the the set is also closed under addition in order to be a left ideal?
No, I didn't bother. I guess that's true.
Okay. Yeah, I think it's just a matter of this. What is it? You know, a star b plus b star a is less than or equal to a star a plus.
Yeah, I
b
guess
star b
that is
thing,
true. So if a plus b, which way are we going? This is supposed to be in I. So we need to show that this is true. And yeah, sure. If this is, we can, without loss of generality, assume a and b are positive. And then this is going to be less than or equal to a star plus b star. No, that's a lie. Okay, well, we'll just leave that as an exercise. It shouldn't be too hard.
Yeah, I don't think you even need to assume they're positive. It's just when you expand that out, you'll get like a star b plus b star a, and then you know that's always below a star a plus b star b.
Yeah. Okay, so as a corollary, every closed, so every ideal, by which I mean closed two-sided, is hereditary. So this doesn't even really need a proof. I mean, we saw that, so I in particular are a left ideal, but it's also self-adjoint. So this is hereditary. Okay, moving along. If A is a simple C star algebra, which means that A has no ideals, then every hereditary subalgebra is also simple. So this is quite a nice feature. Hereditary subalgebras actually inherit a lot of their traits from their containing C star algebra, for example, simplicity. Okay, so first, let's just assume we have an arbitrary subalgebra, a C star algebra, not necessarily simple. The point is that ideals in the subalgebra will be generated by ideals in the algebra A. And these will be all of the ideals that we get. So we claim that I intersection B is an ideal in B. So first of all, it's clearly closed, and it's going to be closed under multiplication, addition, and adjoint, since both I and B are. So it's certainly a C star subalgebra. We need to show that it's an ideal. So let's take some B and I intersection B and C and B. Well, then, BC, that's clearly in B, and it's clearly in I because it's an ideal. And obviously the completely analogous thing tells us that CB is in I intersection B. So indeed, it is an ideal. Now suppose that we have an ideal J in B. We need to find some ideal I such that J is equal to I intersection B. So we'll take ourselves an approximate unit. This is a perfectly reasonable set. And in fact, it's going to be an ideal. So that's not so difficult to check, since U lambda observes things from B. And of course, for multiplying things by A, we still land in this set. So we want to show that J is I intersection B, but I guess, okay, that's pretty clear. Since any B, whoops. By definition of the approximate unit. Okay, so that concludes the section on hereditary subalgebras. And next we'll talk about functionals and representations of C star algebras, with the goal of probably in the next lecture getting to the GNS construction, and we will see that all concrete C star algebras are in fact, all abstract C star algebras are in fact concrete C star algebras. So recall that a concrete C star algebra was a closed self-adjoint subalgebra of B of H for some H. Well, so we will see that so we can always represent a C star algebra in some Hilbert space. And to do that, we need to talk about functionals and representations. Okay, so if we have, this might have been mentioned before, but if not, if we have two C star algebras, and phi A to B a linear map, we call phi positive if it sends positive elements in A to positive elements in B. So first thing to note is that, of course, a star homomorphism, which is certainly a linear map, this is B being just the complex numbers, then we call this a positive linear functional. Sorry about that. I'm back. My computer crashed there, or my internet did rather. I guess it doesn't like two things on Zoom at once, but it's going to have to deal with it. Okay, then we call phi a positive linear functional, which is the subject of the next few theorems. Okay, first thing to note, since any self-adjoint can be written as the span of two positives, we see that any positive linear functional, or more generally even any positive map, will send self-adjoints to self-adjoints, or for a functional, this means that the self-adjoints land in the reals. And similarly, since we can always write any element as the sum of two self-adjoints, linear combination of two self-adjoints, and phi is linear, we get that the star of an element, and then you take your linear functional, this just gives you the complex conjugate. So these have a lot of nice properties, but bear in mind they are not star homomorphisms, they're not characters, they're not going to be multiplicative in general. Okay, so a few definitions. If we have a positive linear functional with norm 1, then we call it state. These are very important. If our functional satisfies phi AB equals phi BA for every A and B, then we call it traceable. And of course, we can also have the combination, which would be a traceable state. So understanding the state space and the traceable state space of a given C star algebra is usually an important thing to do. We will denote SA to be the state space. And it won't be such it won't be much, we won't use this much just yet, this traceable state space, but again, it's often a very important component of your C star algebra, so why not define it here? Okay, and then just one more part of the definition. A state is said to be faithful so it's faithful. I mean, sometimes this will mean that it's injective, but here that would be way too much to get an injection into the complex numbers, but we do call it faithful if A star A gets mapped to 0 if and only if A itself is 0. So let's see some quick examples here. So when I say tracial state, you might think of traces on matrices, and indeed that would be a good thing to think about because that is our first example. So if we have the n by n complex matrices and we take some matrix, then we can define the normalized trace to be 1 over n times the sum of the diagonal elements. This is a faithful tracial state. And in fact, it's the unique tracial state on Mn. The fact that it's faithful is not difficult to see because Mn happens to be simple. You can check that anything that gets mapped to 0 like this would be an ideal. And we'll actually probably see that later. So it's useful when you're thinking about how C star algebras should act. You think matrices on the one hand and commutative C star algebras on the other hand. So what do we have for commutative C star algebras? Well, of course, any functional on a commutative C star algebra will be automatically tracial because where did this go? A and B themselves will commute. So everything is tracial. What else? So I already mentioned that these sort of look like characters, and indeed any character is a state. But not all states are characters. So more generally, let's take a Borel probability measure. On X. Then we can just integrate with respect to this measure. Maybe I should have told mu there. This is a tracial state. The fact that it's a state is because we chose a probability measure, so you can, of course, get more general functionals by relaxing that condition. And we often think of tracial states as non-commutative measures. And probably later when, for example, if Tristan discusses tracial states on certain groupoids, it'll become clear that these are somehow very much linked to measures. Okay, another example. So we saw what happens on finite dimensional Hilbert spaces. Let's see what happens on general Hilbert spaces. Oops, it's just one example. So take your favorite Hilbert space, take your favorite bounded operators. This defines a positive linear functional on B of H. And it won't be traceable unless H is finite dimensional. Okay, so these are some nice examples to have in mind when we're talking about these things. Now let's go back to the more general case of just arbitrary C algebras. And here we see again that we don't need to assume any sort of continuity condition when we have a positive linear functional. This is similar to what we saw for star homomorphisms. So any positive linear functional on a C algebra is bounded. Okay, so let's try to prove this by contradiction. So suppose this is not the case. Then there exists some C-star algebra which has an unbounded linear functional. Let's take that C-star algebra and then linear functional. Okay, now if phi is unbounded, then we can find a subset of the unit ball that sees this unboundedness, so such that the absolute value of phi to the n goes to infinity as n goes to infinity. Since things are composed of positive elements without loss of generality, we can assume that each an is in fact positive. And passing to a, okay, so yeah, if this were not true, then since everything is made up of positive elements, it would be bounded, and we're assuming not. Okay, and then passing to a subsequence, if we have to, we can assume that these absolute values are always greater than 2 to the end. Okay, So let's define an element A. So I should say, why is this actually well defined in A? Well, it's because we're assuming that these guys are in the unit ball. So they have norm at most 1. So indeed, this will converge to something in A. So for all n and n, we have that phi A this is greater than right. So this is always larger than n, which is, of course, a contradiction. So this is using positivity in our C-star algebra. Okay, good. So all linear functionals are automatically bounded if they're positive. We also have a nice Cauchy-Schwarz type inequality for our functionals. Which is probably where we'll stop today after proving this. So to see why this is not so unreasonable, if we're thinking about positive linear functionals as somehow being akin to what we see here for linear functionals on B of H, and we know that our inner product on B of H will satisfy this Cauchy-Schwarz inequality, then we might expect that this to be true for more general positive linear functionals on C-star algebras, and indeed it is. Okay, so this is a positive linear functional. If we happen to have that phi of A star B is 0, well, it's clear. So this is always going to be a positive element here, and certainly 0 is less than a positive element. So we can assume otherwise. Okay, since phi is positive, it sends positive elements to positive real elements. We see that by our characterization of positive elements in C-star algebra, that this is greater than or equal to 0 for every lambda in C. Now, in particular, this is true for lambda equal to T phi A star B absolute value over phi B star A. And that's for any real number T. So we want to plug in this this lambda into here and expand it out. And what we get, I suppose I will spare the glorious details. You're free to check them, of course. It's just plug in and expand. What we get is that actually, let me, in the interest of time, just even. So since we're nearly out of time, let's just say that plugging everything in, we get that T squared phi A star A plus 2T phi A star B plus phi B star B is greater than 0. Okay, so if we happen to have that phi of A star A equals 0, then we get that phi of B star B greater than minus 2T phi A star B for every T in R, which is impossible. So we can assume that phi A star A is non-zero. And we can let T be minus phi A star B absolute value divided by phi A star A. And again, plugging everything in now, plugging T in here now, we get that phi A star B squared over, phi A star A minus 2 phi A star B squared over phi A star A plus phi B star B. So this is all greater than 0. And therefore, moving everything around, we see that this means that phi which is what we wanted. Okay, so I'm just a bit out of time, so I'll just say that next time we'll see how functionals give us representations. And by representation, we just mean a representation of a C-star algebra as a concrete C-star algebra. So see you next Tuesday, and I will hopefully not have the same connection issues, and apologize for that. Okay, thanks. Bye-bye.